Okay, so after that investigation, notice that we're always comparing each of the quadratics to y equals x squared. So y equals x squared is like our base, it's like home base, and then y equals 2x squared is something a little bit different. It's like, well, what happened there? Or y equals 1/2 x squared is something, so we're really just subbing in values here to the a term, and we're kind of seeing what happens. So when a was greater than 0, or sorry, this should say, actually, I should change this. This should say greater than 1. Can we change that? Sorry, guys. Good start. So this should say a is greater than 1. So what happened when the a value was greater than 1? So what happened when it was 2? Well, I think what happened was we had something called a vertical stretch. The parabola became a little bit more narrow, or more skinny, I guess. Not that it's a competition. It got stretched out a little bit. Now, when it says here, when the a value was greater than 0 but less than 1. So what that means is essentially between 0 and 1. So when a value was a fraction, we had this thing called a vertical, again, it's a vertical compression. It's the opposite now. It's a little bit more wide. And then when when a is negative, what happens? Right, when that leading coefficient a is negative, it seems to reflect on the x-axis, in which case we say opens down. So we'll say reflects on x-axis, and really what we mean by that is faces down. Okay. So now, maybe based on this new information, we can almost kind of fill in this table. And I'm not sure if you wanted to just go ahead and maybe use Desmos here. You could use Desmos to fill in this table, or just based on the investigation, you kind of maybe know what's going to happen here. So remember, we're always comparing everything to y equals 1 x squared, or just y equals x squared. This is what we call the basic or parent function. In grade 11, you're really going to hear that term parent function quite often. Now, we're trying to think of this quadratic here, y equals 3x squared, okay? Now, the a value, it is certainly greater than 1, and it is positive. So how about the direction of opening of this? Because it's positive, we know that this thing's going to open up. And was it a stretch or a compression? Well, I think it's a stretch because the a value is greater than 1. So the shape of the graph compared with y equals x squared, is it a little bit more wide, or is it a little bit more narrow? So I think this one would be more narrow. Yeah, that's a much better word. Okay. Maybe we'll fix that. Narrow. Okay. How about y equals 0.5 x squared? Is this going to be opening up or down? Up. Thank you. And is this a stretch or a compression? Compression. Absolutely, because it's between 0 and 1, right? So this one right here. And that means this one's going to be a little bit more wider. Now, when we're talking about the a value here, this a value is just the number. Like I know you might say, okay, this is negative 0.4, and it truly is. But you almost have to, when it comes to transformations, you have to kind of separate the negative from the 0.4 just for a moment. Because the negative, what this negative does all on its own is that it'll change its parabola from opening up to opening down. That's what the negative does. So we'll say opens down. Now just look at the 0.4. Whether it's a positive or negative 0.4, it won't matter because either way, it's still going to compress. And therefore, it becomes wide. Lastly, and I know, -7 is well below 0. I know. But just take the negative away from that 7 just for a moment, because that negative will make this parabola face down. And then that 7 right there, don't look at it as -7. Look at it as just 7. So this 7 is going to stretch the parabola. Therefore, it is more narrow. Fair? Folks, before I move on to anything, does that sit okay? Yeah? We're not shocked by that? Okay. Sorry, the reason why I'm asking is because in the past, we've only had 2 units of quadratics. And this year, what I've done with this new textbook is that I've split the two, like each unit, I've just kind of split them up, almost like a meiosis. Hey, science people? Yeah. And there's now 4 units of quadratics. Okay. So, maybe we can investigate as to why this is happening. It says, consider the following relation, y equals 2x squared. And the first thing they want us to do here is to fill in this table of values. We say, okay, no problem. So we know, y equals 2 times something squared. And what we're going to do is pull out our calculator and just fill in the values. And it's really, really quick. Now, this says make a table of values from -3 to +3. And that's what I have here for you. So we'll say 2 bracket -3, close the bracket, squared. And we get 18. I got 18. Now, without getting rid of that, without clearing that from your calculator, you're going to go and get rid of the -3 and pop in a -2, and you should get +8. Over here, you should get 1. Sorry, 2. When you put in a 0, well, I mean, you should just get 0. And then because this is parabolic, we should get the same idea here, 2, and then 8, and then 18. Yeah? Okay. -3, +18. -2, +8. -1, +2. 0, 0. 1, 2. 2, 18. 3, 18. Sorry, 2, 8, 3, 18. Lovely. And we should try our best to connect without making it look like a V. Like that. Okay. Now, it says here, starting at the vertex, calculate the step pattern. So we're going to start here at the vertex, and every time we go over 1, the way we go up or down becomes our step pattern. So we'll say, okay, over 1, notice we go up 2, so +2. Over 1, 1, 2, 3, 4, 5, 6, +6. Over 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, +10. So our step pattern, I'm going to call that SP. Our step pattern is 2, 6, 10, ... And you might remember step pattern from Unit 3, or maybe not, because it was a little while ago. But usually, the step pattern on a basic quadratic would be 1, 3, 5, 7, 9. Remember, it's all the odd numbers. So it says here, what do you notice from the original step pattern of y equals x squared? So the step pattern of y equals x squared was 1, 3, 5, ... I think 3 is enough there. And our new step pattern, so we can say step pattern of y equals 2x squared is now, well, 2, 6, 10, dot, dot, dot. What do you notice between the two-step patterns? Yeah. Is that a handout? Yeah. Yeah, the original step pattern seems to have this multiple of 2. So you've taken the original step pattern and you've multiplied each of the steps by 2. So maybe we can write that. So what can we, how can we write this down into real good words here? The original step pattern is multiplied by 2. Every single piece of it. Can you see that okay? I lost my page extender. I don't know what happened. Go to tools, more tools. Thought it was around here. I lost it. It's gone forever. Okay, they want us to do the exact same thing with this new quadratic, y equals negative 3x squared. So in our calculator, we go y equals negative 3x squared, and we try our best here to fill in these values and do it efficiently. Negative 3 bracket, negative 3 close bracket squared, and we get something like negative 27. We go back, get rid of the negative 3, put in negative 2, negative 12, type in a negative 1, and then 0 should be 0, and then positive 1, positive 2, positive 3. So we've made our table of values from negative 3 to positive 3, and we're going to just now graph this. So negative 3, negative 27, negative 2, negative 12, negative 1, negative 3, 0, 0, bam, bam, bam. Okay, try to draw in your smooth curve as best as you can here. Okay. Starting at the vertex, let's calculate this step pattern. Now just be careful because this y-axis is actually counting by 3s. So although we'll go one box is worth 3 on the vertical axis. So over 1, look, we went down 3. Over 1, down 3, 6, 9. Over 1, down 3, 6, 9, 12, 15. So our step pattern here is negative 3, negative 9, negative 15. Now, how does this compare to the original step pattern of y equals x squared? Well, y equals x squared has a step pattern of 1, 3, 5, and then it goes on, of course. And then our step pattern for negative 3x squared is negative 3, negative 9, negative 15, dot, dot, dot. Folks, what do you notice about the two-step patterns? Is there anything? Yes, each step, the 1, the 3, the 5, is being multiplied by negative 3. So each step is multiplied by negative 3. Now, is that a coincidence, you think? We're essentially taking that a value. In this case, the a value is -3. And what we're doing is we're taking the original step pattern and we're multiplying it, each step, by -3. And if you look closely on the previous example, that's exactly what happened in y equals 2x squared. We took the original step pattern of 1, 3, 5, and we just multiplied each step by 2. Now, thankfully for us, every quadratic that's written in the form y equals ax squared, you even notice in the investigation, is that their vertex is always 0, 0. So when it comes to graphing quadratics, I think that the table of values, although it is the most powerful way to graph, it truly is, we can almost sort of retire it if we have two pieces of information. One, we need the vertex, and two, we need the step pattern. So it says here in example 4, graph using the vertex and the step pattern. So because these two quadratics are written in the form y equals ax squared, the vertex is always 0, 0, because there is no vertical shift, vertical movement, and there's no horizontal shift or any horizontal movement, So first thing we're going to do here is state the vertex. Our vertex is 0, 0. Now, our step pattern. The way in which we calculate the step pattern is by multiplying that original step pattern, 1, 3, 5, by whatever the a value is. So we're essentially doing this. 1 times a, 3 times a, 5 times a, and then it'd be 7 times a, and so on. But I think 1, 3, 5 is enough. So what we can do here is now say that our a value we know is 0.5. So we're going to substitute 0.5 into the step pattern formula here, and we can kind of come up with our own. I mean, this step surely can be done in a lot of your heads, and that's great, but I do want you to show some steps. Okay. So our step pattern is now 0.5, 1.5, and 2.5. So we're starting at 0, 0. Here's our vertex. And we're going to go over 1 and then up 0.5. Now, just be careful here because this is counting by 1s. I know it looks like it's counting by 2s, but it's skipping 1 each time. So we're going to go over 1, up 0.5. And then from here, over another 1, and then up 1.5. So it's the little 0.5 and then a whole 1. And then over 1 and up 2.5. So 1, 2.5. So this is what our quadratic begins to look like, something like that. Now, don't forget the other side here. Over 1, up a half. Over 1, up 1.5. Over 1, up 2.5. So you can see how narrow this quadratic truly is here. And again, maybe we can outline the step pattern here. Over 1, up 0.5. From that point, over another 1, up 1.5. Over 1, up 2.5. Sorry. Question? It is. It is, yes. That last dot here is that the coordinate is 3, 4.5. Okay, and then the next one. We'll do this one maybe in purple. Our vertex, because it's written in y equals ax squared, our vertex is at 0, 0. Now, our step pattern is based on the a value, and in this case, it's -2. So we're taking that original step pattern, 1a, 3a, 5a, and we're subbing in -2 into each step. So it's really 1 times -2 3 times negative 2, 5 times negative 2. And we'll get negative 2, negative 6, negative 10. So that becomes our new step pattern from the vertex, of course. So we're plotting our vertex. We're going to go over 1 and then down 2. Great. Over another 1, down 6. Over another 1, and then down 10. Same idea over here. Over 1, down 2, over 1, down 6, over 1, down 10. Folks, any questions about that? Good? Okay. Last one here. In this sort of way, they kind of go the opposite on us. They say describe the transformation or transformations that were applied to the graph y equals x squared to obtain the new graph. So y equals x squared is what we always sort of compared to. Y equals x squared has a vertex of 0, 0, and its step pattern is 1, 3, 5, and so on. So when we look at these particular quadratics, we kind of got to think of, well, because we know the vertex here, it's just going to be written in y equals ax squared. Yeah? But we need to determine the a value. Because that a value is the thing that we multiply the step pattern by, we can almost just look for the step pattern in these and find or determine the a value. So in this first one, we know the vertex is 0, 0. Now, we're counting, it looks like this vertical axis is counting by 4s, so be careful of that. So there's a good point, and I'm not sure, is that a good point there? Does that look like an okay point? Or no? So we're going, looks like it's over 2 and down how many? What is that? 4, 8, 12. So what do you think? Folks, there's a lot of talking going on. I don't know why. What are we going to do here? The first coordinate is not a nice one, is it? We go over 1 and then down a little bit. So we had to go over 2 and right down to 12. How might we get this a value? What do you think? Yeah. Divide both of them by 2. Well, the thing is, the step pattern in y equals, well, not ax squared, just y equals x squared, is 1, 3, 5. So like this is the first step, this is the second step, this is the third step. Yeah? So we have the second step of this, so this 3 is really now a negative 12. Yeah? So how might we get this a value? Dividing the 12 by 3, and what do we get? Negative 4, yeah. So what we did was we took this negative 12, we're dividing it by 3, and we get negative 4 as our a value. So this quadratic must be y equals negative 4 x squared. Now, how about this one? We're counting by ones, twos, three. It's really nice. We're starting at the vertex. We go over 1, and then it looks like we go up 1, 2, 3, 4. Right? So our original step pattern here of y equals x squared is 1, 3, 5, dot, dot, dot. But ours, that first step, ended up being a positive 4. Now it's really nice when you have the first step there because we now know that the a value is just going to be positive 4 because the 4 divided by the 1 here is just 4. So we can say, okay, the equation of this is y equals 4x squared. Now I don't have my page extension. Okay, oh, it's here. Okay, it wanted us to kind of write in the transformations.
So if we say, okay, the transformations of this one, the first one would be that it reflected on the x-axis. The second transformation was that it got stretched or vertically stretched
By a factor of 4.
This one over here,
Compared to y equals x squared,
there was no reflection, but there was a vertical stretch.
by a factor of 4.
You see, that's what I thought too, but sometimes it could look like this should be compressed. It really does look like it because it's a little bit wider, right? But if you look at this step pattern here, and this axis is actually counting by 4s, meanwhile the other one's counting by 1s, it seems like it should be compressed, but really the numbers tell us that. It just feel like the odd look, yeah. Well, that's the thing. When we're stating the transformations, we kind of got to separate the negative from the 4. So the negative does the first one here, it reflects it in the x-axis, and the 4 stretches it. That makes sense? Folks, we got some homework here. It's on 256. And let's give this some time here.